Good afternoon, everyone. Welcome to today's SANCOLD YPF webinar, and thank you for joining us. I'm your host, Ashley Kutsia, the YPF chair at SANCOLD. Today's session focuses on data acquisition systems for geotechnical dam monitoring, together with practical case studies demonstrating their application in real-world projects. Before we begin, I would just like to make a few housekeeping notes. All microphones and cameras have been disabled to minimize background noise and ensure a smooth session. The session is also being recorded, and you are welcome to post your questions in the chat, but we will have a short question and answer session at the end where you will be able to raise your hand, and then I will enable your mic for you to answer your question directly. It is my pleasure to introduce today's presenter, Patu Magada. Patu is a sales engineer in infrastructure at Campbell Scientific Africa, specializing in data acquisition and monitoring solutions for geotechnical and infrastructure applications. He holds an MBA as well as a Bachelor of Earth Science in Mining and Environmental Geology, and brings experience across the mining, civil engineering, and infrastructure sectors. Patu's work focuses on bridging technical solutions with client needs, acting as a trusted advisor to engineers, consultants, and project stakeholders. His strengths lie in solution-driven consulting, technical application of monitoring systems, and long-term relationship development. Patu, thank you for joining us today. The floor is yours.
Thank you very much. I'm going to proceed and share my screen.
Thank you. We can see it and hear you clearly.
Not so responding on my side. Oh. I don't know what could be the problem. It's not projecting. Are you able to see the full screen?
Yes, I can see the screen. Maybe you can just share again.
All right. Okay. Hi, everybody. My name is Patu Magada. I am a sales engineer for infrastructure, Campbell Scientific Africa. I welcome everybody to our webinar. I hope you are going to enjoy our engagement on Campbell Scientific data acquisition system for geotechnical.
Patu, we can't see your presentation.
Okay, let me do this. The issue and sharing by. All good, Ashley?
Yes, I can see now. Maybe go to the next slide.
Apologies with regards to data. Welcome everybody once again to our discussion on Campbell Scientific Data Acquisition System for Geotechnical Dam Monitoring and the related case studies that we have in the market. Ashley has done a very good job in putting the introduction. I'm not going to repeat my introduction. Before we dive into our discussion, would like to give a little bit of overview of Campbell Scientific. Campbell Scientific was founded in 1974 by Eric and Evan Campbell in Logan in the USA. The company early direction was strongly influenced by soil science, which highlighted the need for automated, precise field measurement. So it is a privately owned and it has manufacturing facilities in Logan in the United States. Our equipment are deployed globally in almost all continents in the world. Including we have a weather station in Mount Everest. Our data acquisition system will also deploy in the space shuttle. So we have more than 20 global offices and more than 725 employees, all with capabilities in engineering and environmental science to ensure that they are able to serve the market in all technical requirements the market needs. So this provide a well-dedicated resources to serve the market globally. So the markets that we serve include dam monitoring, which is forming part and parcel of our discussion today. Structural health monitoring, environmental monitoring, weather stations, and renewable energy. On this slide, this is a demonstration of the first data logger that was founded by Campbell Scientific in 1975. So this is a low energy data logger which was developed on the technology called complementary metal oxide semiconductor. So it is portable and is able to deployed in the field for a long time due to its ability to not consume a lot of energy. So on this slide, I'm demonstrating how rugged our monitoring platforms are. So many of Campbell's scientific systems are built to operate across wide environmental temperatures, ranging from high to the lowest. For example, here, just as I've indicated, we have a weather station that was deployed in Mount Everest, which is the very coldest, and we have the weather station that was deployed in UAE, which is very hot. So, and it's able to stand such harsh environmental conditions. This is how data logger, how our meteorological station will look in the field. We have a rain gauge, we have a wind speed and direction, enclosure, we have temperature and relative humidity. So the important aspect of meteorological station is how this meteorological station has impact in dam monitoring. For example, real-time meteorological data are necessary to check rainfall intensity and duration, which are fed into rainfall runoff models to calculate expected reservoir inflow. So to better manage the data bet that this will be very crucial in managing the dam, having the information regarding the reservoir inflow. And then we have a compact digital weather station. It's all in one digital station which measure most of the parameters you will find when you're measuring a weather station, such as wind direction, rainfall, wind speed. So it is all in one. You don't have to have different sensors when you have this one. So let's now dive into our agenda of the day. We will discuss the importance of dam monitoring. Why is it important for us to monitor dams? And the 10 steps that need to be considered when designing a monitoring system. We will also tap into the vibrating wire technology, which is also known as VSPEC rather, and the case studies that we have in the market. The main question that we will need to answer when we are addressing the people that control the finances of funding the project is, why do we need to monitor? Why is monitoring important in respect to them? So monitoring is important because we need to catch the unseen. So some parameters are not be able to be seen by our eyes. So when we identify those parameters, we are able to manage the risk and reduce the dam failure, which can cause unanticipated changes, which can destroy the property, destroy the life. So we also need to monitor to ensure that our structures are performing in line with the international standards. So actively monitoring the dams will ensure that the assets that we deployed in the field are in good state and they are safe to use. And when we do that, we're able to compare the trend that we have, the current data that we have versus the historical data. And by so doing, we can be able to see if there are any changes in terms of structural failure, or if the structure is still intact. So when we monitor, we also meet the regulatory requirements by providing accurate data. We don't provide guesswork. We need to provide accurate data to ensure that we comply with the regulatory bodies, and this will also give us a chance to determine early warning if there is a system failure, and then advise the public in this regard. I'm now going to discuss 10 steps that are required or that need to be followed when we are designing a data acquisition system, to ensure that the data acquisition system that we are designing, it meets our requirement, and we are able to get the data that we want. In most cases, we just end up acquiring the data system, no matter how expensive it is, but it end up not addressing the needs that we have in the field. So there is a quote by John Dencliffe: "Every instrument on a project should be selected and placed to assist answering a specific question. If there is no question, there should be no instrumentation." So the the first and most important aspect in data acquisition design, we need to define system objective. We need to identify the specific question the data need to address. Are we concerned with water level? Is there a concern about slope stability? And having done that, we will be able to choose the right sensors that, for example, talk to water level monitoring, that talk to slope stability, seepage. So we will then be able to be in a good position to do that. And then when we have addressed these two aspects, we'll then need to determine the data that is applicable for this project. When we select the data, we need to determine which data will be able to handle specific sensor inputs, and how the data will be able to process how the data logger will be able to process the data itself. And then we have to choose communication channels. The communication channels need to meet or need to be aligned with the site condition. We need to ask ourselves several questions. Do we have a good network in the site? Do we have a good line of sight for us to use radio communication? How far is the data loggers in a station? How far are they from one station to another station? So all these factors, they play into part in selecting the right communication channel. So we also need to design the power system align with the site condition. Most of these sites are allocated, or rather are allocated in areas where there is no power supply. So we need to determine, because when we are monitoring the data, there must not be any power disruption. Otherwise, if there's a power disruption, there will be a problem in our data integrity. So is the site located in a remote area where there's no power? Then in that case, maybe we might need to use solar power. Equipment enclosure is very important. We need to select equipment enclosures that will ensure that our data logger, the battery, and all other relevant components are able to fit. We must not select equipment enclosure that is too small, otherwise it will cost us big time. Or select equipment enclosure that is too big, and then we will have spent a lot of money on something that is not applicable. In most of these sites, there is the requirement for civil work because of the mounting structures that are needed. We need to define all the civil works that are required and ensure that we have the right people to accomplish this type of task. When it comes to installation, it is very important. It is of paramount importance that people with the right skills who are competent in data acquisition system installation are selected, because if we even if the data acquisition is good, and if it's not installed properly, it won't be able to accomplish its task. When it comes to data management, we need to determine requirements such as storage requirement and the way in which data should be presented to all relevant stakeholders. And then we need to be around the table and discuss other consideration that may limit the deployment of the data acquisition in the field. So, and be able to see if we can tackle such considerations. So, as we have said, the first step is to define the system objective. How will the data acquisition system help us make decision. And who is interested in the data acquisition system. So we need to define all relevant stakeholders who have interest on the data acquisition system and be able to accommodate them so that when we present the data, it meet their needs. How soon and after how long should the data be collected? And how long should the data need to be reviewed? So when we ask all these questions, we will be able to choose the right brain for processing the data, our data, and ensure that we are in a good space. Who needs to access to the data, and as these stakeholders that have interest, how far are they located from the site? In some instances, the stakeholders or decision makers are located. We have a project where in Ethiopia where the stakeholders and decision makers are located about 700 kilometers from the sites. They are sitting somewhere in Addis Ababa. So we need to be able to select a data acquisition system that will allow remote monitoring. So if that data acquisition does not allow remote monitoring, it will mean that they will have to be going to the field now and then to collect the data. So that data acquisition system must be able to meet this requirement in this regard. So what parameters can be monitored that will help make decision? How long should the system be operational? We need to select the system that is rugged. Most of these infrastructure projects are designed to last for 50 years. So we need to select a system that is aligned with the longevity of the infrastructure projects. How can data be presented? Is data going to be presented in visual format, or is it going to be in graphs? So all these issues must be tackled from the get-go, and by so doing, we will be able to be in a good space to move to the next step, which is sensor selection. So when it comes to sensor selection, we need to make a right decision. For example, measurement at single point or at distributed across large area. For example, when we talk about single point, piezometer is one of the good example for single point measurement. Because, for example, if it's measuring ground water pressure at a specific depth, so it's a good example of a single point sensor. So whether the sensor will be distributed across area, so that need to be determined. And we also need to pay attention as to whether the project at hand, is it a new project or old construction? Why is this important? Because some sensors need to be embedded on the concrete. So you cannot embed a sensor on a concrete in an old construction, because that will affect the structure of that particular construction. So if the construction is old, then that may obviously require minimal drilling to have that sensor to measure. What sensor will provide the engineer? What kind of engineering outputs will the sensor provide? Will the sensor change the environment in which it is monitoring? Because some sensors, for example, thermostats, they operate with the current, and as a result, they can raise artificial temperature, causing the temperature to rise, whereas it's coming from the sensor itself. Can the sensor require to be serviced after installation? That is a very important aspect of selecting a sensor, because if you have a sensor that will require will require to be serviced now and then you will be disrupting your monitoring. So how long does the sensor will require calibration after installation? Those are important questions we need to ask. We need to ask before we select the sensor. Aspect of warranty and accuracy, recalibration. So we need to also ask our colleagues in the market to understand what works better in this regard. Does the sensor supplier have proven reputation? That is very important. Will they provide service? Aftermarket service is very important. So if we have those questions addressed, we'll be able to make right decision when it comes to sensor selection. So we have in geotechnical monitoring have different sensors. So our system at Campbell Scientific are able to measure sensor, most of the sensors that are supplied by a third-party supplier. So if you are interested in pore water pressure, you will have vibrating wire piezometers. When we talk about deformation or settlement, we need to have inclometers. Stress and strain, we have VW, strain gauges and load cells. Stability, we have tilt meters, crack meters, and accelerometers. So these are the sensors that are mostly applicable in geotechnical monitoring, and in particular dam monitoring. So when it comes to sensor selection, again, there is analog or digital sensors. For example, vibrating wire is analog sensors, how long the sensor. So one of the aspect that is very important is cable length. So most of the time a client will approach us, they want a data acquisition system that will be connected to a piezometer, and they don't give us a cable length. So cable length is very important, and because if we don't get that right, it's gonna be problematic when we have to connect that into data logger. The communication channels are what will ensure that you are able to receive your data. Without communication channel, then you are probably not going to have automated data in a remote area. So we need to, in selecting the right communication channel, we need to ask ourselves several questions. How often do communication need to happen? How often do you need to see data? How quickly should you know about the alarm condition? What communication technology exists at the site? We've talked about site condition. If the site has a network, if the site has good line of sight. For radio, what communication option won't work on site? So redundant communication needed? Do you have staff trained that can manage communications? So even address that, you will be able to choose the right communication channel necessary or suitable for your site condition. We have different communication channels available in the market. We have USB, which is the old-fashioned, and the USB is not able to provide remote monitoring. It's only limited for local communication. This is where you plug your computer directly into equipment and read and collect the data. So that will require you to go to the field you need to go to the field, and sometimes the conditions are not favorable. It might be raining, and then you might end up skipping imported data. So we have a cellular, which is the option available for communication. You need to ensure that the area where the site is has a good cellular network to be able to choose this communication channel. It has challenges of monthly expenses. You need to ensure you have sufficient subscription to data to ensure that you are receiving your data without disruption. We have a satellite. So we have satellite. The challenge with satellite is that it is very expensive and it's limited in data transmission, but it allows communication to occur in remote area. So another common communication channel is internet. It is very cost effective, and it allows data to be presented in real time. So if there is an internet in the mine and in the dam, then it can be integrated into the already available system. The disadvantage of that is that it requires existing network. The communication channel can also happen through wireless. If the area where the site is as a good wireless, then the communication channel can happen through that. We have radio. We'll also discuss radio separately. We also have RS485. We have fiber optic. We have RS232. So in this slide, we are discussing the communication channels that offer wireless communication channel. So these are wireless communication channel. It include radio, cellular, satellite. So if we're choosing this one, we need to determine the total cost of ownership versus the cost of not having data. So when we don't have enough data, then we won't be able to make a right decision. We won't be able to monitor our structural conditions of our dam in a way that is reliable. So just as we indicate, manual communication tend to be limited in a way that we tend to miss certain data. So this is where we need to choose between the total cost of ownership versus the cost of not having data at all. In this slide, it's example of where we were working with a client to choose a line of sight. In this regard, this site was going to use radio communication channels. So we used Google Earth. We knew where each station was going to be on the basis of the location points that were given to us, and then we were able to measure from one station to the nearest station to a proposed area where the control room is gonna be. So this is gonna be our proposed control room. We need to ensure that the control room has AC power that is reliable. Otherwise, then if the AC power is not reliable, it can be backed up by solar power. And then this is a repeater station, another repeater station. All the stations represented in white will communicate to this repeater station, and then the station on the blue will communicate to this repeater station. One of the important aspects of line of sight is that line of sight changes over time. If you check on the picture on your right, you will see that at first there was clear line of sight, enabling the radio to communicate from this building to the other building. But over time, the vegetation started growing. So this means that now the line of sight is no longer the same as it's no longer the same as it was. So this is a very important aspect when you designing a radio communication system. You need to consider that the line of sight changes over time. The vegetation started growing, and then they cause of obstruction in terms of the radio communication system. This is the example of radio communication that we normally use here in Africa. It does not require lessons. It's called RF422, and it's able to communicate with 4G LTE. It can be added on the repeater station so this cellular 215 can be added on the repeater station to ensure that there's a remote support from Campbell technical team. So if this, for example, there's an issue when this cellular 215 4G LTE is added on the radio communication, we are able to log in and see where the issue is coming without having to come to the sites. This RF422, it can go up to 5 kilometers depending on the antenna and line of sight. So now let's go to that data logger selection, some consideration to put in place when you selecting the data logger. So you need to determine the number of sensor and communication that are required in the site. For example, we have if you have a single channel, this is suitable for when one variable is measured, and we also have multiple channel support. This can support wide range of sensors. We also need to determine whether there's going to be a static or dynamic measurement. So how long will the system operate? All this need to be considered when you are choosing the data logger. So if you look on your right, you have CRVW3. This is designed with 3 sensor input, and it's suitable for geotechnical small geotechnical project. This is mainly applied where sensors are grouped into 3. So you can use this data logger in a situation where you have multiple of sensor, and those sensors are mixed, and maybe at some point you will need to expand your sensor. For example, a CR6 can be expanded. If you use all channels, you are able to expand it. So, but in this case, with CRVW3, you cannot be able to expand it. So, and also CR6 is programmable such that it can be programmable to accommodate analog and digital sensors at the same time. So we have different data loggers displayed here. We have Granite series, we have CR6, we have CR1000XE. So you need to assess your situation and choose the data logger that is applicable in your site. For example, the main difference between CR1000XE and CR6 is the terminal architecture. CR6 Future Universal Terminals, meaning that it can be software configured to accommodate either analog or digital sensor. This include a vibrating wire. So on the other hand, CR1000XC, it has fixed terminals. So it have dedicated terminals for analog sensors and dedicated terminals for digital sensors. So, and CR1000XE cannot measure vibrating wire sensors. For you to measure vibrating wire sensor with CR1000XE, you need AVW vibrating wire analyzer that can be connected to CR1000XE. And then this AVW 200 analyzer, it future VSPECT technology, making it suitable for dam monitoring, bridge monitoring, and all other infrastructure project. And the other part is Granite data logger. This is a high performance data logger that is able to measure at a very high speed. We are talking about 20 hertz or 10,000 hertz, depending on the configuration and the requirement. So when we say 10,000 hertz, it's equal to 10 times. It's equal to 1,000 times per second. So this is how fast it can go. So this is mostly suitable for vibration measurement, seismic measurement, because such measurement require high performing data loggers. And then this is a VW analyzer. The VW analyzer is a tool that we have to check the health of the sensors. If the sensors are still in good shape, if they're still measuring the reliable data, VW analyzer is the right tool that we use to perform quality control, ensuring that the moment the sensor is placed in a ball, its data integrity is confirmed. So we have a case study of a customer that came to us. They were not getting reliable data from their sensor. So now they wanted to overhaul the sensors and replace them with a new one. We advise them to say, no, before they do that, let's first come to your site and audit the sites and check if all these sensors are still in good. It could be that the data loggers were not connected properly, but the sensors are still in good, because most of the time the sensors will still be able to measure what it intends to measure. So we try to save their cost by not allowing them to overhaul their sensors and replace with the new one. We say to them, let's first do the audit with the VW analyzer. And once that is done, then you will be able to we'll send a report to you, and that report will be able to tell you if certain sensors need to be replaced or not. So the other last aspects for data acquisition design is power system, equipment enclosure, civil works, and installation. So you need to assess the site and determine the power requirement for the sites. We have already said that some of these sites are located in remote areas where there's no access to electricity. In this regard, you will need a solar power station or solar power to ensure that there's no disruption in the measurement. And you need to determine the battery and the solar power size for that measurement. Equipment enclosure, we have already discussed that. Civil works, the requirement for civil works, what requirement are those? Understand what will happen at the site. Is the location good year round? You need to assess the climate of the site. When do they normally receive rainfall? So that when you do your installation, you don't have unnecessary disruption. Because at the end of the day, the equipment must be kept dry and grounded. So we talked about ensuring that you have qualified field technician for your installation. That is very important because even a good system can be ruined if bad installation occur. So data management system, data management is important. It's very important. You need to assess who are the stakeholders, what interests do they have in the data, and how's the data is going to be shared amongst those stakeholders. Is the data going to be in real-time monitoring or schedule analysis? Does the data accomplish the original data that you define from when you start the project? All these aspects need to be defined and assessed. So at Campbell Scientific, we have software ecosystem, we have Loganet. This is the primary administrative software for managing networks and collecting data. We have RTMC Pro. This is mainly for creating real dashboard and visualization of dams status. So we have Logalink. This is mostly used by technicians. It's used on the cell phone mobile app to check the health system of the data system on site. And we have cloud integration compatibility. This our Campbell scientific cloud integration is compatible with platforms such as Oxstone for stakeholder visualization. So we have Oxstone. Oxstone is a modern cloud-based monitoring platform designed for infrastructure, construction, mining, and environmental projects. So regardless of the data acquisition manufacturer, Oxstone is able to be integrated and ensure that your data is visualized, managed for all your infrastructure construction environmental project from a single platform. So cloud-based data management. So you need to ensure that your data can be accessed anywhere, anytime on a browse-based interface without a need of having to install software. Ensure that your data is viewed in real time and is it can be accessed on the internet so that people that are remotely based are able to manage that data. Ensure that your data is automated. With automated data, it's important also to diagnose the health of the sensor. In this respect, with our technology respect, automated data is able to do that. We have different vibrating wire sensing technology that are designed to measure different. I think we have already discussed some of these at the very beginning. We have piezometer, strain gauge, with pressure cells, we have crack meters, settlement in place, in kilometers. So they measured, for example, piezometers will measure your pressure, water, groundwater pressure, pore water pressures, and then we'll also measure water level, load cell deformation, displacement, and as well as strain and the temperatures. So there are many challenges that that we come across when we are measuring data, especially for construction environment such as dam monitoring, where the environment is noisy. So the question is, how do we overcome that? We have challenges such as signal interference. There is suspiciability of electromagnetic noise, such as moving trucks, generators, power line. In some instances, sensor aging. Over decades, the internal wire can loosen or relax, leading to weak signal. Also, analysts spend excessive time cleaning noise coming from this signal interference. So, and that results in data fatigue. And it also resulted in unstable data. Cable limits, some data is lost due to lengthy cables. So how do we overcome that? We have a technology called VSpec. So VSpec is Campbell Scientific patented VW measurement technology. Its ability is it has ability to measure signal to noise ratio, noise frequency, allow the continued use of sensor for decades, even if internal wire relaxes over time. So it provides 10 times measurement precision compared to traditional methods. And it ensures that there is clean data in real time because it is able to automatically filter electrical noise and thereby eliminates the need for manual post-processing. So with VSpec technology, there's no need for post-manual processing of eliminating external noises. So it able to ensure that there's extended community. For example, superior noise rejection allow for significantly longer cable run than previously possible. So with VSpec, longer cable run can be possible. Let's dive into our case studies that we have in the market where Campbell Scientific was involved. We have Mosul Dam. This is the largest dam in Iraq. So in this regard, Campbell Scientific was involved in the safety monitoring of Mosul Dam by providing instrumentation, hardware, and software for automated data acquisition system. In this regard, Campbell Scientific CR6 and multiplexer was selected as the main data acquisition system to collect and process real-time measurement for over 400 automated instruments that were based on the dam. So the dam was built on the cast foundation, and the consultant that was involved in the project who selected Campbell Scientific was US ACE monitoring system. We also have Itapu Dam. This is the dam that bordered Brazil and Paraguay. This dam, Campbell Scientific started measuring in that dam from 1996. We have 24 of a CR10X system that are measuring, and we upgraded to 30 CR6 system to measure 1,200 sensors. We also have 3 George dam. In this dam, AWV200 was selected as a preferred vibrating wire sensor interface due to its reliability and accuracy in high electrical noise environment. AWV200 monitor, in that dam, it's currently monitoring hundreds of piezometers, crack meters, displacement sensors, strain gauges, tilt meters, and strain meters. Another dam that we have is the dam called, I can't even pronounce this one properly, is Doshak Dam in the USA. It's a USA Army Corporation of Engineers. So in this dam, Campbell Scientific has CR6 AVW200 multiplexer measuring 630 sensors in real-time monitoring. So let's look at some of the case studies that happen regarding the dam failures. We have this Banku Dam. This dam was constructed in 1951 and it was completed in 1952. The first day total precipitation exceeded 4 inches, like it exceeded 1,000 millimeter, surpassing the area's total annual precipitation by some of 1/5. The dam began to collapse shortly, resulting in the death of 9,600 lives were lost due to the dam failure and the collapse in this regard. Jacksfontaine's tailings dam, this is very familiar to most of us here. It's here in South Africa on 11 September 2022. The dam wall collapsed due to structural failure. The outcome of this disaster is one of the is that one life lost, 1 missing, 76 injured, as well as 51 houses destroyed, and 103 people severely injured. As we know, Jacksfontein is a historic diamond mine located in the province of Free State, and is known in the 1870s as a diamond rush town. So this is a summary of some of the dam failures in the history and the fatalities that occurred due to these failures. So we can see if proper monitoring is not put in place, we can end up costing lives. People can lose their life in this regard. So it is important that we monitor and select the correct data acquisition system for our dam monitoring in preventing situations like this. So predicting and preventing dam failure with early warning of invisible failure. So dam often fail due to internal pressures like seepage, poor water pressure, built up, or foundation movement that are not visible with our naked eyes. So if sensors like water level or tilt sensor exceed a predefined safety limit, the system can automatically send alerts via SMS, radio, or satellite to engineer. This platform can be programmed to trigger a physical response, such as automatical opening of spillway gates to prevent overtopping during extreme floods. So Campbell scientific data acquisition system are designed for harsh, remote, remote environments and run on they run on a lower solar system, ensuring they remain operational even if the main power grid fails during a disaster. This will ensure that there's reliability in the data. There's a data integrity. There's no disruption in the data management. So also long-term health diagnostic is very important to compare historic data with the current data and be able to determine the trend in the structural stability of our dam. And this is the end of my slide, or rather my presentation. We'll now hand this time for questions. I have my colleague Amanda, who's with me, who will assist in answering questions. Should there be any questions? I know this environment is very technical. Some questions I may not be able to answer. So Amanda will come and join on my side to assist in answering. And thank you for your participation and your collaboration in the discussion. Thank you so much.
Thank you, Patu. Really appreciate the insightful presentation. I will give some chance for the questions to come in. If you have a question, you can raise your hand and I will activate your mic. For now, we have a question in the chat, 2 questions in the chat. It's from Dr. Kitsia. He's asking, Patu, from your field experience with Campbell Scientific Systems on large infrastructure like dams, what are the most common grounding and lightning protection design mistakes that lead to instrumentation failure? And what specific design details do you recommend to avoid them? I think let's answer question 1 first, and then you can go on to question 2.
Okay, perfect. Amanda will assist. Amanda is the sales manager for infrastructure, EMEA region. She's based in Canada. She's here in South Africa visiting the clients. She will be able to assist with most of those questions. Amanda will join me.
Hi,
Amanda,
everyone.
I have activated your mic, but it's fine. You can join through. Yeah, thank you. Did you catch the question?
I did. Yes, thank you. So we can never underestimate people's ability to be very creative in everything, including in how they ground the systems. So we've seen all sorts of different approaches. Doctor, I'm unable to pronounce this name, so I apologize, but I'll just stay a doctor. There are several challenges that we have faced. People sometimes leave. I would say that perhaps the most common one we've seen is just not properly burying what needs to be buried and leaving it perhaps too shallow to the point that it's not actually doing the service of grounding it. We've seen a lot of lack of maintenance in that as well. That leads to just grounding not working how it was supposed to. So I think when it comes to grounding, it's important to really understand, first of all, where it's going to be installed, right? And the criticality of what's being monitored and the system, and have proper design for that, burying the system as a whole and connecting it through the best approaches, data loggers, sensors, however it's needed. In terms of the second question, I apologize. Let me take a little look here.
I can read it. It says, for distributed dam instrumentation with long cable runs, do you recommend single point grounding or multi-point grounding? And how do you prevent ground loops while still protecting against lightning-induced surges?
I think that is both can work very well, but it would depend on how distributed those actually are. I should say I'm not really a specialist in grounding per se. I'm more of a specialist in the applications, being a geotechnical engineer myself. What I would encourage, Doctor, perhaps I would perhaps suggest you to send us an email, and I can get you in contact with someone who's much more knowledgeable than I am on this, if that's okay. Because grounding is very specific, and I'm not the best person to respond to this question.
Okay, thank you. We got a thank you response. I would just like to know if anyone has any other questions. I don't see any more in the chat. Would someone like to raise their hand? We have a question in the chat by Germano. He's asking, can we use Campbell's VW analyzer to censor from other brands?
Yes. The simple answer to that is yes. So it's a VW analyzer. It's an instrument that we use for auditing. So it doesn't matter where the sensor is coming from. So we design our system in such a way that they accommodate third-party sensors. So yes, the answer is yes.
Right, thank you. I don't see any hands. I'll give a few seconds for the chat. Okay, I think that is the end of our session. I just have a few final closing points to make. Thank you, Part 2, for an insightful and practical presentation. It is clear that effective data acquisition and monitoring systems are fundamental to inform decision-making and long-term dam safety. So yeah, I really appreciate you coming out and sharing your knowledge with us today. And I hope that this will be a continued relationship between Campbell Scientific and SANCOLD.
Thank you so much for providing us with the platform. Yes, definitely. We are looking forward to opportunity for continuous engagement and find a common ground in areas of collaboration.